In this video, you'll learn how computers store binary numbers physically. We're going to cover all the topics you see listed here. Timestamps for chapters are in the description, so feel free to skip to whatever you're looking for. Be aware though that some concepts in this video build upon each other. Okay, that's it, let's go. Let's take a simple mechanical switch. It has two states, off and on, but we could interpret them as 0 and 1. Arranging multiple switches then allows us to represent multiple digits of a binary number. What we want, however, are electronic switches that we can manipulate without any mechanically moving parts. And, as it so happens, there's an existing component for that called the transistor. Transistors come in a variety of different packages, like the ones you see here. And there are also different kinds of transistors, regardless of their packaging. For our purposes though, let's just look at a MOSFET, or metal oxide semiconductor field effect transistor. It has 3 pins. They're called the source, gate, and drain. The gate controls the state of our transistor. When less than some threshold voltage is applied to our gate, then the transistor is in its off state. In this state, no electrons can flow across the source and the drain. However, if we apply a voltage higher than the threshold voltage, then the transistor is in its on state. In this state, electrons can flow between the source and the drain. In other words, the gate controls whether the transistor is open or closed, just like a switch. Now you may be wondering, how can there be billions of these inside a computer? Turns out, we can make components like transistors microscopically small thanks to semiconductors. Let's take a material made up of nothing but silicon atoms. As you can see, we have 4 valence electrons in the outer shell of each of our atoms. When I move these atoms close to each other, they form what's called covalent bonds by sharing these electrons with their neighbors. Now what if we introduce another kind of atom into our material? This process is called doping. Let's dope our material with phosphorus, which has 5 valence electrons. Notice that we still have our bonds just as before, but we have an extra 5th electron over here. We have just introduced a surplus of electrons into our material. Adding even more phosphorus atoms would give us an even higher surplus of electrons. This type of material is called a N-type semiconductor. Now what if instead of phosphorus we introduce a different element? Let's take boron, which has only 3 valence electrons. This time, there aren't enough electrons to form all 4 bonds. We are essentially missing an electron over here, which means there is a hole that wants to be filled. Electrons may fill this hole, causing another hole to open up elsewhere. Effectively, this means our holes can move just like electrons can. This type of material is called a p-type semiconductor. Let's take both our N-type and our p-type material and put them next to each other. The area between both is called the p-n junction. Free electrons of the N-type material will try to move into the p-type material and fill holes. And the holes will therefore move towards the N-type material. This eventually creates an area called the depletion region, because there are no excess electrons or holes available in it that could move. This region acts like a barrier that stops electrons from moving across it. Now ask yourself, what happens if we apply a voltage to all of this? If we attach the positive terminal to the N-type material, you can see that electrons are moving towards the positive terminal and holes are moving towards the negative terminal. Therefore, no electrons are able to flow through this device. However, if we flip the positive and negative terminal, the opposite happens. Electrons and holes are both forced towards the depletion region. This allows them to overcome it and we get a current to flow through. What we've just built is called a diode. This component lets electrons flow through one way but not the other. As you can see, semiconductive substrates can be used to build electronic components. And because it all depends on the properties of atoms, we can make these components insanely small. So how does a transistor work? Let's take a p-type material and put some n-type over here and here, then add 2 pins into them. On top of all this, we'll place a layer of oxide followed by a layer of metal. As you probably have guessed, we now have the source, gate, and drain of our transistor in place. Due to the depletion regions forming at the p-n junctions, no electrons can pass through. However, applying our threshold voltage to the gate creates a channel that electrons can pass through. And that's all there is to it. That's our transistor. Now we're going to look at actual devices that use transistors to store binary numbers. RAM is short for Random Access Memory. Memory implies that it stores a bunch of numbers, and random access refers to the way we read and write these numbers. It comes in a variety of different forms, such as DRAM, SRAM, or VRAM. We're going to talk about these separately, but first let's look at what they have in common. First, RAM is generally volatile. That means when our RAM is not attached to some power supply, it loses all of its data. This downside of RAM comes with an advantage, which is speed. RAM is much faster than most non-volatile devices, which we'll talk about in a little bit. Now, what does memory mean? As I said, memory is just a big pile of numbers that are stored in a device. Here I have grouped them into bytes, or 8 binary digits, to make them nicer to look at. Usually we prefer to view memory in hexadecimal, as it's more compact. So why is it called random access memory? Imagine our memory was stored on something like a magnetic tape. To get to a specific number on this tape, we would first have to wind it to the correct location, right? So if we wanted to read this number over here, we'd first wind the tape from the beginning all the way to it. Then to get to another number, we might have to get all the way to the end first, wrap to the beginning, and then keep counting from there until we get to our number. This is called sequential access, because we're only able to access our number in sequence. However, again, RAM is random access memory. This means we can arbitrarily read and write our numbers in any order we want. As our computer needs to access many different locations in memory quickly and all over the place, this property is very useful. DRAM stands for Dynamic Random Access Memory. You've probably heard people refer to a computer's memory, or main memory, or system memory, or similar terms. In all of those cases, they're probably talking about DRAM. A stick of DRAM is also called a Dual Inline Memory Module, or DIMM, and it looks like this. On it are multiple integrated circuits that contain our actual memory. But how does that work? How can our numbers be stored on these chips? First, let's look at how a single binary digit, or bit, is stored on a DRAM memory cell. We're going to need a transistor and a capacitor. By the way, a capacitor is just a component that's able to store an electric charge. We're going to take this capacitor and attach it both to our transistor and to ground. Next, we'll add what's called the word line and the bit line. Think of these like wires that are used to read and write the data from our memory cell. And note that these are not connected to each other. So right now, our capacitor does not hold a charge. The state of our memory cell is therefore 0. Increasing the voltage on our bit line turns it high. However, no current can flow into our memory cell because the transistor is currently off. We can open the transistor by activating it using our word line. Now a current can flow into our memory cell, charging the capacitor. Its state has therefore changed to 1. Then, if we leave the bit line low and set our word line high, this activates our transistor, causing the capacitor to discharge itself and setting our cell state back to 0. As you can see, the bit line decides whether we are writing a 0 or a 1. And the word line is used to open the memory cell and write that value. We can also read the state of our cell by measuring the voltage at our bit line. Of course, a single memory cell is not very useful. So in our DRAM, we have grids of memory cells just like this one. Our rows and columns are the word lines and bit lines. To read or write data, we activate one of the word lines. And the bit lines are used to either measure or set each column's state, which performs a read or a write. All of this requires further circuitry which is attached to our grid of memory cells. For example, we need a row decoder, sense amplifiers, and a multiplexer. These are used by the memory controller to access our cells. Given a memory address, the row decoder figures out which word lines to activate. The sense amplifiers are used to measure and amplify the voltage differences on our bit lines to read or write data. And the multiplexer is used to select which bit lines are actually connected to our input or output. And even this is an oversimplification. We just care about how the data is stored. Another thing worth mentioning is that we don't have a single large grid of memory cells. Instead, each chip on a DIMM contains many of them. DRAM also has a big problem. Our transistors and capacitors are microscopically small. That sounds like a good thing, but capacitors can leak their charge. And because ours are so small, they do so very quickly. To avoid losing their state, each memory cell must be refreshed constantly. And this brings us to the big upsides and downsides of DRAM. DRAM cells use few parts, just a transistor and a capacitor. Therefore, DRAM is relatively cheap to manufacture. DRAM is also very dense. This means we can pack a large amount of cells into a very small space. The downside is, like we just talked about, DRAM needs to constantly refresh itself, and this significantly impacts its performance. Then DRAM also has some fancy terminology attached to it. For example, you'll hear about SDRAM, or synchronized DRAM. DRAM requires a clock signal to operate. Older variants of DRAM were asynchronous. That means the clock updating DRAM was not synchronized to the rest of the system. In synchronized DRAM, on the other hand, the clock signals are synchronized. Pretty much all modern forms of DRAM in your computer are actually SDRAM. Another term is DDR, which stands for double data rate. There are multiple versions of it, which each further improve performance. Let's look at the first version of DDR. Here's a diagram of our clock cycle used by the SDRAM. See how our clock signal has a rise and a fall? Double data rate SDRAM utilizes this by performing data transfers during both the rise and during the fall of our clock signal. This doubles the rate at which we can read or write data. DDR2, 3, and 5 all utilize an internal clock used by the DRAM. By altering this internal clock, they're able to prefetch more data, which further improves performance. DDR4 is unique in that it does not double the amount of prefetched data. Instead, it arranges its banks, which you can think of as our memory grids from earlier, into groups. Each of these groups contain multiple banks, which can be accessed simultaneously and therefore improve performance. SRAM stands for Static Random Access Memory. The primary difference compared to DRAM is the design of its memory cell. We replace the capacitor used in DRAM with two inverters arranged in a loop. Then we add another transistor and a second bit line. The two transistors, just as before, allow us to open and close the memory cell. What's important to note is that our inverters are actually connected to a power source internally. This allows them to retain their state even when the cell is closed. Also, as you can see here, there are 4 transistors making up our inverters. By the way, an inverter is just a circuit that outputs the opposite of its input. If we supply it with a 1 using our bit line, it outputs a 0 on the other side. And if we supply it with a 0, it outputs a 1. By arranging them in the way we did, we've created a feedback loop. And this is what's storing our cell state, just like the capacitor did in DRAM. We can use our bit line to read the state of the inverter loop, or we can force its state to 0 or 1. Of course, we can then arrange these cells in a grid and all that fun stuff, but we've already covered that with DRAM. And the advantages and disadvantages of SRAM should also be pretty clear. As the cells are now internally powered, we don't need to refresh them anymore. So compared to DRAM, SRAM is significantly faster. The downside is that we use more components to build SRAM, making it more expensive. And each cell requires more space, which makes it less dense than DRAM. For these reasons, SRAM is used in places where we need less densely packed data with very high performance. An example of this is the CPU. The computer's central processing unit is what manipulates our data and makes things happen. But to do this, it needs to be able to temporarily store data in its own memory that lives directly on the CPU. For example, we have caches which store data that can be reused by multiple operations. And it keeps registers, which are small pieces of memory used by the operations. Both of these are made up of SRAM because performance is critical here and we're dealing with much smaller amounts of data. We're going to talk more about the CPU in a separate video, but that's basically it for SRAM. VRAM stands for Video Random Access Memory. You already know how it works because VRAM is actually just a kind of DRAM that lives on your graphics card. On it, we have the GPU, the Graphics Processing Unit. GPUs are really good at processing a lot of numbers, specifically floating point numbers, in parallel. Where does it keep these numbers? In VRAM. For one, VRAM is physically closer to the GPU. Additionally, the memory bus, or basically the pathways connecting the GPU to its memory, is typically much wider than that used by DRAM. So when we do things like render a three-dimensional scene, we transfer all relevant pieces of data, such as geometry, textures, and so on, into VRAM. From here, the GPU can access our data efficiently and do its thing. Over the years and in different kinds of devices, the actual design of VRAM can vary. The most common kind of VRAM used in most modern graphics cards is called GDDR. While different technologically, just like DDR-SDRAM, it achieves higher performance with each iteration. There are other technologies too, for example HBM or High Bandwidth Memory. It features vertically arranged DRAM dies and has significantly more pathways connecting it to the GPU. Because of this, these pathways aren't just printed on a circuit board like with GDDR, but require semiconductors called interposers. But honestly, I don't know enough about these technologies to go into more detail. Also, this is not an engineering video, we only care about the basics. So again, VRAM is just a specialized kind of DRAM that lives on your graphics card. ROM stands for read-only memory. As the name implies, this kind of memory can be read from, but not written to. Typically, ROM is programmed during or shortly after manufacture. Then other devices use this ROM and can read data from it. One big difference between ROM and RAM is that ROM is non-volatile. That means it keeps all of its data even when it's not receiving power. You may already be familiar with the term, by the way. Not only are there CD-ROMs, but if you've ever emulated old video games on a modern computer, the files of games that were shipped on cartridges originally are usually referred to as ROMs. That is because in old video game cartridges, the game's code, graphics, music, and so on were all stored on a ROM chip. The console would then read data from this ROM to actually run the game. And, fun fact, this other chip here is actually SRAM. It's used for the save data of the game, and that's why there's a battery in here. Remember, SRAM is volatile, so without the battery, it wouldn't keep the save data. Anyway, the kind of ROM used in game cartridges like this is called mask ROM. Its data is built into the chip during manufacture. Let's start with a grid of word lines and bit lines and build some ROM using diodes. Remember, diodes allow electricity to flow through one direction, but not the other. With diodes in our grid of cells, if we activate one of our word lines, watch what happens. Wherever there's a diode, current will flow from the word line into the bit line. In other words, at each diode we are going to find a 1. Measuring the voltage on each bit line then allows us to read our data. Pretty simple, right? We can do the same with other components such as transistors. Here each transistor is connected to ground. This looks a little bit like our DRAM cells from earlier, but they're missing the capacitor. First we set all bit lines to 1. Then we activate the word line. Now notice how the word line activates the transistor, which then redirects the flow of current from the bit line into ground. This turns those bit lines low, representing our zeros. What makes these approaches really nice is that they're incredibly simple. A single component per memory cell, or none at all, is all we need to represent data. The downside is that only the manufacturer is able to write the data. So this is a little impractical. Once our ROM is manufactured, that's it. There's no way to change the data. PROM stands for Programmable Read-Only Memory. This kind of ROM can be programmed in the field rather than by the manufacturer. Let's go back to our diode matrix from earlier. Again, we have a nice grid of data. Here, every cell is a 1 because they all have diodes. But now let's add a fuse to each cell. This fuse is how we're going to program our ROM. When we receive the PROM chip from the manufacturer, this is what it looks like. Now what happens if we use the word lines and bit lines to target specific cells and apply a really high voltage to them? We're gonna blow the fuses. By doing so, we can selectively destroy our memory cells and turn them from a 1 to a 0. And that's it. We can now build a special device that selectively blows fuses to program data into this chip. However, once the fuses are blown, they can't be repaired easily, so we pretty much can only program things once. After that, the device is truly read-only. EPROM stands for Erasable Programmable Read-Only Memory. This variant uses a special kind of transistor called a floating gate transistor. What makes this transistor special is that it has a second gate. This gate is completely surrounded by the oxide layer. The transistor works like it always does, however we can do something really cool with it. If we apply a much higher voltage than usual to the gate, some electrons will be able to penetrate the floating gate. This creates a negative charge inside the floating gate. Now if we have a negative charge in the floating gate, this increases the threshold voltage of our transistor. In other words, we now can't activate the transistor unless we apply a somewhat higher voltage to it. Now if we arrange a bunch of these transistors in our usual memory grid, here's what we get. Next, we force electrons into our floating gates. Here the yellow gates have electrons in them, and the white ones do not. If we set each bit line high and activate a word line, look what happens. Transistors with a charge in their floating gate are not being activated. That is because we trapped electrons and increased the threshold voltage of those transistors. So the voltage we've been using to activate our transistors is not enough to activate those ones. Therefore, we now have cells that are 0 and cells that are 1. What makes EPROM even more convenient than PROM is that we can also reprogram it. EPROM usually has a little quartz window in its packaging, exposing the silicon chip underneath. If we put this chip under UV light, we can force the trapped electrons out of the floating gate, resetting the cells to their original state. This is great if we want to make a change to the ROM at a later time, or if we want to reprogram it because we made a mistake. EEPROM stands for Electrically Erasable Programmable Read-Only Memory. The only difference between EEPROM and EPROM is that EEPROM uses another kind of transistor for its cells yet again. It uses what's called a FLOTOX, or Floating Gate Tunneling Oxide Transistor. As you can see, the floating gate is elongated towards the drain a little bit. What this does is it gives us the ability to electronically erase the state of the floating gate. Depending on the voltages on the drain and the gate, we can either force electrons into the gate, or we can force them out. With this, we've gained the ability to reset the state of our transistors using electricity rather than UV light. The cell layout with these transistors also looks a little more complicated. We start with the same layout we used for the EPROM, except that our transistors are FLOTOX transistors. Then we add a second transistor for every cell and a second word line for every row. These allow us to select which particular floating gates we would like to erase. Compared to our EPROM, that means we don't have to wipe all ROM at the same time. We can just reprogram specific cells. If we oversimplify it, early flash memory is basically a kind of EEPROM. However, it isn't considered to be read-only. This kind of storage is found all over the place. SSDs use flash memory, old USB flash drives use it, SD cards do too. This stuff is everywhere nowadays. The cells still use the same transistor, although there have been more technological advances. We'll get to that in a second. First, let's look at how memory cells are laid out in flash memory. There are two arrangements called NAND flash and NOR flash. In NAND flash, transistors are connected in series. In NOR flash, transistors are connected in parallel. NAND flash is more dense, which actually makes it cheaper to manufacture. On top of that, NAND flash has faster erase cycles and can write data faster. NOR, on the other hand, is faster at reading data and has individually accessible cells. And finally, NAND flash is less reliable than NOR flash when it comes to endurance. What I mean by that is that NAND flash is more error prone and generally has a shorter lifespan due to the way NAND flash writes its data. However, some of these problems are minimized by the memory controller where possible. Depending on the use case, NAND or NOR flash can be the right fit. If you're manufacturing an SSD, for example, NAND flash is your go-to choice. If you're trying to store a program for your microcontroller, then NOR flash might be better suited. Memory in both NAND and NOR flash is separated into distinct sections. Let's look at a hypothetical NAND flash, for example. We have multiple dies, which contain the actual circuitry of the NAND flash. Let's say we have 4 dies in our example. These 4 dies then contain 2 planes. Both of these can be operated on simultaneously. At least that's how I understand it. Each plane contains thousands of blocks. Let's say we have 2048 of these. Blocks are the smallest unit we can erase. So if we erase data, we erase an entire block at once. And finally, our blocks contain pages. Say we have 128 of them in each block. Each page then contains some kilobytes of data. Let's say our pages are 16 kilobytes in size, which means we'd have 16 kilobytes times 128 pages times 2048 blocks times 2 planes times 4 dies. And all of that adds up to 32 gigabytes of data. Then NAND flash has another really interesting technological advancement. Remember our cells are floating gate transistors that trap charge inside of their floating gate? What if you store different amounts of charge and differentiate between them? That's what this technology utilizes. Some NAND flash use what's called single-level cells, or SLC, which store 1 bit per cell. This is kind of what we've been used to so far. Its successor, the multi-level cell, or MLC, stores 2 bits per cell. This means it can differentiate between 4 voltage levels. A TLC, or triple-level cell, stores 3 bits of data, which means there are 8 different voltage levels. And a QLC, or quadruple-level cell, stores 4 bits of data, which means it can differentiate between 16 voltage levels. The downside is that higher-level cells are less reliable. They are more prone to errors, and their lifespan may be shorter than that of flash with lower-level cells. Single-level cells suffer less from these problems, can perform faster, and consume less power. Another technology is called 3D NAND flash, or VNAND, or some kind of combination of these terms. As the name implies, it arranges our memory cells not just on a flat grid, but vertically as well. This animation here is not very accurate. In reality, these layers are manufactured vertically into silicon with a variety of complicated techniques. But the basic idea behind it is that it utilizes the available physical space more efficiently, allowing us to store more data without having to make our cells any smaller. This is a hard disk drive. It is, of course, another non-volatile storage device, which means it keeps its data without power. As the name implies, it contains a disk. Or actually, it contains a stack of disks called platters. Both sides of these platters are covered in a thin layer of magnetic material. Note that the disk itself is not magnetic, just the thin layer on the surface. During operation, this stack of platters rotates at a rapid speed. The HDD also has a stack of arms, one below and one above each platter. These are moved by the actuator to reach across the surface of our platters. The tip of our arm is called the read and write head. Its job is to magnetize tiny sections on the surface of our platters or to read their current magnetic state. Each platter surface is divided into thousands of tracks, and each track is just a ring around the surface of the disk. These tracks are then further subdivided into sectors. Note that there are many more sectors that I've highlighted here. Typically every 512 bytes or something stored on the disk form a sector. So this visualization is very oversimplified. If we take one of our tracks and imagine it as a straight line, we can look at it in more detail. On this track, we magnetize very small sections to write state. This process is called magnetic recording. The states can be recorded alongside the surface, like here, which is called longitudinal recording, or we can magnetize perpendicular to the surface, like this, which is called perpendicular recording. We could call these states left and right, up or down, or whatever, but for simplicity I will visualize the states as positive and negative instead, just because that's easier to look at. Now you might assume that these are our bits, maybe negative is a 0 and positive is a 1. Sadly, that's not the case. It turns out that the read and write head doesn't actually measure the magnetized parts on the disk. Instead, it measures what's called flux reversal as it moves across the platter. In other words, it measures the transition from positive to negative, or negative to positive. Therefore, if there's no change, we have a 0, and if we detect a transition, we have a 1. This kind of encoding is also called non-return to zero inverted, or NRZI. But again, this is not what most HDDs actually use to encode their data. The signal that is picked up by the read and write head is usually further encoded using different techniques, but that's beyond the scope of this video. Just know that our magnetic states don't represent bits directly. Another magnetic storage medium is magnetic tape. I'm sure you're familiar with music or video recorded on tape as analog signals. For example, we had our good old cassette tapes or VHS tapes and so on. But magnetic tape also has been used for digital storage of binary numbers. The concept is fairly similar to our hard disk drive, except that it has no spinning platters, but a roll of magnetic tape. The tape can be rolled from one reel to the other. An electromagnet can then sense our magnetic states, or at least the flux reversals, or it can write new states to the tape. To do this, there's usually some kind of opening, like with this cassette tape, we have an opening at the bottom. Also, as the read and write mechanism does not come with the tape, we need a separate drive to perform the reading and writing. And unlike other devices, magnetic tape is sequentially read. Remember, to get a specific piece of data, the device first needs to wind the tape to that location. Magnetic tape also comes in a variety of form factors. For example, you've probably seen these old school reels of tape that were used by really old computers. And again, of course, we had cassette tapes. But we also have modern tape cartridges. It may surprise you, but magnetic tape is not actually a dead technology. These cartridges can store dozens of terabytes of data. And compared to an SSD, for example, they retain their data for significantly longer. Anyway, finally we have the floppy disk. Inside a floppy disk is a thin disc-shaped sheet that can store magnetic states. The difference to our hard disk drive is that the floppy can't actually rotate the disk by itself. It needs a floppy disk drive to do it for it. That's why there's a hole in the middle. This is where the drive holds onto the disk to spin it. And again, like the hard disk drive, the disk has multiple tracks of data that can be written to. And these tracks are also divided into sectors, which again is oversimplified in this visualization. There are many more of them. This tiny hole over here matches with a hole on the disk. This can be used as a reference point to identify the current rotation of the disk, although the actual data on the disk can of course be its own reference point. This longer hole here is where the read and write head can read or write data. It basically just exposes the tracks on the disk. And finally, up here we have a little notch. This can be covered up to mark the disk as read-only. Like the small hole before, the drive can detect if this hole is covered or not. However, this is like a hint for software to treat it as read-only. Technically, this does not physically stop writing of data. And finally, floppies come in a variety of form factors as well, from the larger 8-inch to the compact 3.5-inch packaging. We can also store data using light. This is called optical storage. You know, CDs, DVDs, Blu-ray, those are all optical storage media. Unlike hard disk drives and floppy disks, we only have a single track on the CD. It covers the entire disk like a spiral. And of course the disk is rotated inside of a disk drive, which may read data from the disk. Let's take a closer look at the surface of a CD. Imagine this line as the surface of our disk. Above the disk, we place this contraption here. Up here, we have a laser emitting device. Down here, we have lenses that focus the laser onto our disk. And the green box on the right is a sensor which can detect light. Let's activate the laser and shine a beam of light onto our disk. The light is then reflected back into our light sensor. Fair enough, so we can detect light reflected off our disk. But what happens if we make a small dent inside a tiny spot on the disk? Because of the dent, the light is reflected with less intensity, and our sensor picks up less light than before. And this is how we differentiate between two states. Let's add multiple dents on the surface of our CD. The term used for flat surfaces is lands, and the dents are called pits. Anyway, as with the hard disk drive, non-return to zero inverted, or NRZI, is used to represent our bits. Again, this means pits and lands don't represent zeros and ones. Instead, the transition between them represents a 1, while no transition represents a 0. You may be asking, where do these pits come from? Now for a CD-ROM, these are actually etched into the CD during manufacture, which is why it's ROM, read-only memory. But what about CDR, which is once writable by the consumer, or CDRW, which can be repeatedly rewritten? These disks don't actually use pits and lands. For once writable CDs, the disk has a layer of die. Using a laser, we can create permanent markings on this die using high temperatures. These marked areas then reflect less light than the untouched die, allowing us to store two states. Repeatedly rewritable disks, on the other hand, use an alloy that can be one of two solid states. At certain temperatures, the alloy is in a crystalline state. When heated to around 500 to 700 degrees Celsius by our laser, it changes into an amorphous state. Both of these states are maintained after they are burned onto a disk. And as you may have guessed, they also reflect light differently, which we can detect. What's cool though is that by heating the material to about 200 degrees Celsius, we can revert the alloy back to its crystalline state. That means we can rewrite data repeatedly. And that's it for now. We've covered just about all the most common types of data storage. There is more, of course. For example, there are punched cards and punched tape, and we've only covered everything at a surface level. But if we kept going into more detail, this video would never end. I hope you learned a thing or two, and thank you for watching.